Frontier large language models are protected by layers of safeguards. Our stack attack breaks each layer in the pipeline individually, compromising frontier models including GPT-5 and Opus 4. Developers rely on layers of safeguards to protect their models. A typical pipeline looks like the schematic on the right. User queries are passed through an input filter, a small, specialized model that classifies queries as either harmful or benign. Harmful queries are immediately blocked, whereas benign queries are passed through to the generative model. The generative model itself undergoes post-training to refuse or deflect harmful questions. Finally, the generative model's response is fed through to another specialized model, the output filter, that can block the generation. Variants of this basic approach are used by all the major proprietary developers, including Anthropic, OpenAI, and Google. And our stack attack can break these state-of-the-art defense pipelines. Developers hope to produce a strong defense by stacking multiple weak layers of defenses together. And there's some good logic to this. If provided each defense is independent, then there's an exponential increase in difficulty with each additional layer that you add. The key insight behind the stack attack is that we don't have to break all of these layers simultaneously. Instead, if we can isolate each layer individually, then we can break them sequentially, and this turns what would otherwise be an exponential problem into a linear one. Formalizing this, whether the search space is exponential or linear, depends on whether the components are separable. The components are perfectly separable, which is the worst case for the defender, if an attacker has direct API access to each component. For example, if you also use the input and output filter as moderation API endpoints that users could use in their own applications. Now, on the opposite extreme, the components are perfectly inseparable if there's no way that an attacker could tell which component blocked a query. Now, that sounds nice in practice, but it's in theory, but it's quite hard to pull off due to various side channels in practice. So because of this, we see most implementations are semi-separable. You can't directly access each component, but you can infer which component blocked the query. The stack attack exploits this seemingly small information leak by finding jailbreak prompts for each layer individually. We then concatenate the input filter jailbreak with a template that causes the generative model to repeat an output jailbreak. And then finally, we have the harmful question that we wanted the model to answer in the first place, but we might have modified itself in order to jailbreak the generative model component. So this combined jailbreak bypasses each defense individually. To study this systematically, we constructed our own open source safeguard pipeline. We tried out specialized moderation models like ShieldGemma initially, but found that a simple few-shot prompted model worked best as an input out and output filter. So we went with that for these experiments, but we'd really love to see more work improving the state of the art in open source filters. As a baseline, we attack these pipelines with persuasive adversarial prompts. This is using a large language model to rephrase the prompt using similar persuasive techniques that you might use to convince a person, like appeals to emotion. We also use the confirm attack that iteratively refines a random sequence of tokens into a jailbreak using black box optimization to increase the output token logits corresponding to the desired response. We demonstrate our stack attack using a combination of persuasive adversarial prompts, PAP, and confirm. But there's nothing special about these attacks. In fact, we've instantiated the stack with a whole variety of different jailbreak methods in order to come up with universal jailbreaks in proprietary models like GPT-5 and Opus 4. In this example, we're going to start by using PAP to rephrase a harmful query that even the generative model alone would refuse into one that seems more benign. And this is sufficient to fool the generative model. But our problem is that the input filter is going to block it. And if we somehow lucked out and got past the input filter, then for sure the output filter is going to block the generative model's response. So we need to find a way to jailbreak these two pesky filters. And to prepare to do that, we're going to add two sequences of random tokens, one at the start, one at the end, and there's going to be a repetition template instructing the model to just repeat verbatim this second sequence of random tokens. Now, of course, just adding random tokens doesn't really break anything. The input filter and output filters are still going to reject this query. But what we can now do is apply the confirm adaptive attack. So first, we're going to apply it to this initial sequence, and that's going to optimize this random token sequence into a jailbreak of the input filter. And We're then going to do this again for a jailbreak of the output filter. And this resulting concatenated series of jailbreaks is going to bypass each of the defensive components individually. So that sounds really nice in theory. How does it look in practice? Empirically, we find that this stack attack bypasses the filters 71% of the time, whereas the PAP baseline alone, this solid blue line at the bottom, never defeats the pipelines. So stack can clearly break these pipelines, but even so, safeguard pipelines are not useless. So notably, stack gets even higher, around 80% attack success rate against an undefended model, so just the generative model. And PAP would get almost 100% against that undefended model. And there's an interesting thing that the reason stack does worse here, even though it's built on top of PAP, is that the input and output filter jailbreaks confuse the generative model, degrading the quality of the responses. But we can't just get rid of them because then we'd get blocked by the filters. So it is imposing these trade-offs for attackers that can make the pipeline meaningfully more secure. Now, this attack assumes that we can jailbreak each component individually. So it's a semi-separable or completely separable pipeline. If a defender were to make a inseparable pipeline, you can still do a transfer attack where in this experiment, we developed an attack on a proxy QN3 model that we allowed ourselves full white box access to. And then we transferred this attack to a target model where we had no access to the components whatsoever. And this still achieved an attack success rate of 33%. And then, of course, you could, in theory, use various techniques to maybe boost that success rates even further. So in summary, I'd say safeguard pipelines are genuinely a useful security tool, but they don't solve all robustness issues. And you could easily overestimate how good they are if you were only evaluating them on sort of more traditional attacks that don't take into account this pipeline. Stack has been able to bypass a variety of safeguard pipelines, including those of front-end models, as we describe in more detail in the paper. But safeguard pipelines are still better than an undefended model, and they can be made even stronger with a couple of design tweaks. So the first thing I'd really love to see defenders start doing is make components inseparable. That's really the key to prevent attacks like stack. So for a start, don't tell the user in your API response which pipeline component blocked the query. Some production APIs do this. It makes it very easy for us to construct a stack attack. Let me tell you that. But obscuring it in the API isn't enough for a savvy attacker because we can infer which component triggered from things like timing or other side channel attacks. So if a query is rejected quickly, then it's probably the input filter. If it takes a long time, it's probably the output filter. You can avoid leaking that just by running all of queries through every stage of a pipeline, and you only give output to the user once all of the stages are complete. And if any stage blocked it, you just get a refusal, no more detail. Now, another key thing here is don't expose the models that you're using as filters or closely related models, like things that you capped on fine tuning or had a very similar, ancestor model. And this could be exposed for an open weight release, or it could be through an API endpoint, reusing these filters as moderation APIs. If we do that, then we can just find a jailbreak for that and then transfer it over like in the transfer attack. So make our life harder. Don't give us similar models that we can transfer from. And this leads to sort of a second point, which is that inseparable components are not going to save you if all of your components have exactly the same failure modes and can all be exploited with the same jailbreak. That's just like setting a pin with the same digit. Very easy to guess. So ensure that filters have non-overlapping failure modes by mixing up how they're trained, different data sets, different architectures, use a reasoning model for one, like your input filter, use a classifier head for another, like your output filter. This will make it harder for us to transfer. This was joint work with my wonderful co-authors on this slide. For more information, check out our paper at AAAI or on the archive link below. Thanks so much, and I look forward to seeing more secure pipelines in the near future.